Welcome to the second part of the discussion about auxiliary systems. Since we're interested in many electron systems, we will ask the question, what could a good auxiliary system for a many electron problem be? We have all these interacting electrons, and the interaction causes the problem. The dream would be to have an auxiliary system without interactions. Now we have to tune it, like the position and the width in the example of the box in the last lecture. Namely, we may try to tune the potential. This is the most obvious thing in the general case. We try to tune the external potential. Of course, it is not at all obvious that such a potential always exists. In the example of the box, we have seen that if we ask too much to our auxiliary system, it will not be possible to get the exact answers. But the problem that we have today is just to calculate the density, no other observable. So our question is, for a given material with interacting electrons that has some density, can we find, in principle, a non-interacting system where we tune the potential such that we get exactly the same density? Let us try to see whether there is a major obstacle in principle. So let us replace the interacting Schrödinger equation by a non-interacting Schrödinger equation with an effective, we say, auxiliary potential. And let us think that we want to reproduce a target density. This target would be the density of our interacting system. Now we calculate the density of the auxiliary system, which should give exactly this target density. The density of the auxiliary system is easy to calculate. We can turn the non-interacting problem into a Schrödinger equation for a single electron and calculate its density as sum over squared wave functions. To make the density appear directly in the Schrödinger equation, I multiply the complex conjugate of the one electron wave function and sum over occupied states. Now the density, which we suppose to be given, appears. It simply multiplies the auxiliary potential. And we can now solve the equation for the potential. There is no apparent contradiction in the result, so we can have good hope that this auxiliary potential exists. Of course, the right side depends on eigenvalues and eigenfunctions calculated from the potential. So the problem is self-consistent, and it is not so obvious that one can find a solution. The question whether such a potential exists that allows a non-interacting system to yield the same density as a given interacting one is called a question of representability. Representability questions are difficult ones, and you will hear them mentioned from time to time. But in practice, we really almost never run into this problem for the density, so we can take it for granted that it exists for our purpose. As an outlook, you might be interested in the fact that people sometimes do have the exact density, for example, from a quantum Monte Carlo calculation for simple systems. And they determine the corresponding auxiliary potential, for example, with an algorithm like the one I have just shown you. You can look at this example in the reference if you're interested. For now, take away the fact that it could be a good idea to build a simpler, an auxiliary system from which we can get the one observable that we really need for density functional theory, namely the density. And that the auxiliary system to get this interacting density could be a non-interacting system with a potential that we have to tune in a suitable way. How to do this is still to be seen, so see you soon.